Something is building inside the sun, right now. As you watch this video, a force older than human civilization is gathering strength 93 million miles away. In May of 2024, Earth received a warning. The most powerful solar storm in over 2 decades slammed into our planet. The Aurora danced over Florida, GPS systems failed across the heartland, satellites scrambled to survive. Most people saw the beautiful lights and went back to their lives. They did not understand what almost happened. They do not understand what is coming. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. Something is building inside the sun, right now. As you watch this video, a force older than human civilization is gathering strength 93 million miles away. It has happened before. It will happen again, and when it arrives, it could send our satellites tumbling from the sky like leaves in a hurricane. In May of 2024, Earth received a warning. The most powerful solar storm in over 2 decades slammed into our planet. The Aurora borealis danced over Florida. GPS systems faltered across the American heartland. Satellite operators scrambled to protect their spacecraft. Most people saw the beautiful lights and went back to their lives. They did not understand what almost happened. They do not understand what is coming. This is the story of solar storms, of the machines we have placed in orbit, of the invisible shield that protects us and the terrifying possibility that it might not be enough. We will travel to the heart of the sun where temperatures reach 27 million degrees Fahrenheit. We will examine the delicate satellites that now govern nearly every aspect of modern life. And we will confront a scenario that keeps space scientists awake at night. A cascade of destruction that could lock humanity out of space for generations. The threat is real. The clock is ticking. And somewhere on the surface of the sun, the next great storm is already forming. Chapter 1. The day the sky turned red. May 10th, 2024. A Friday evening in the Northern Hemisphere. Across North America, people are finishing their work weeks. Children are being picked up from school. Families are planning their weekends. Nobody is thinking about the sun. But 93 million miles away, something has already happened. 3 days earlier, on May 7th, a region on the sun designated Active Region 3664 erupted. Not once, multiple times. Massive explosions of magnetic energy tore through the solar atmosphere, each one hurling billions of tons of superheated plasma into space. These eruptions, called coronal mass ejections, were aimed directly at Earth. The plasma is traveling at over 2 million miles per hour. Even at that speed, it takes roughly 3 days to cross the void between the sun and our planet. The ejections are staggered, launched hours apart, but they are converging. By the time they reach Earth, they will arrive in rapid succession. A bombardment. At the National Oceanic and Atmospheric Administration Space Weather Prediction Center in Boulder, Colorado, scientists have been watching. They have been calculating trajectories, running models, and what they see is alarming. This will not be an ordinary geomagnetic storm. The indicators suggest something they have not seen in over 20 years. On May 10th, the first coronal mass ejection arrives. It slams into Earth's magnetosphere, the invisible magnetic bubble that shields our planet from the worst of the sun's fury. The magnetosphere compresses, buckles. The boundary that normally sits roughly 40,000 miles above Earth's surface is pushed inward to barely 20,000 miles. The shield is holding, but barely. Then the second ejection arrives, and the third, and the fourth. The magnetosphere is being hammered repeatedly. Each impact sends waves of energy cascading down toward Earth's surface. Charged particles that would normally be deflected are finding pathways through. They are spiraling down along magnetic field lines toward the poles, and as they collide with atoms in the upper atmosphere, something spectacular begins to happen. The sky starts to glow. In northern Canada and Alaska, auroras are nothing unusual. The northern lights dance across the sky regularly during periods of solar activity. But tonight the lights are different. They are brighter, more intense, and they are spreading southward with remarkable speed. By 9 in the evening Eastern Time, people in Michigan are photographing ribbons of green and pink light overhead. By 10, the aurora is visible in Ohio, Kentucky, Tennessee. By midnight, people in Florida are standing in their backyards staring upward in disbelief. the Aurora borealis is visible at 25 degrees north latitude. This has not happened in over a century. In Mexico, people flood social media with photographs. In Cuba, the lights are visible on the northern horizon. Across the Caribbean, sailors at sea watch colours dance across the water. The entire northern hemisphere seems wrapped in an ethereal glow. For most observers, the experience is magical. They do not understand that they are witnessing a symptom of something dangerous. The aurora is beautiful precisely because it represents energy penetrating our planet's defences. Each photon of that green and pink light is evidence of charged particles that made it through the magnetosphere. The brighter the aurora, the more particles are getting through. The farther south it reaches, the more compromised our shield has become. While millions of people point their phones at the sky, a quieter drama is unfolding in control rooms around the world. At SpaceX headquarters in Hawthorne, California, engineers are monitoring the Starlink constellation. More than 5,000 satellites, each one a compact spacecraft about the size of a table, orbiting between 300 and 500 kilometers above Earth's surface. These satellites provide internet service to millions of customers across the globe, and right now they are in trouble. Solar storms affect satellites in multiple ways. The most immediate threat is atmospheric drag. Earth's upper atmosphere, normally a thin whisper of gas barely worthy of the name, expands dramatically when energized by solar particles. The thermosphere, the layer between 80 and 500 kilometers altitude, can increase in density by a factor of 10 or more during severe storms. For satellites in low Earth orbit, this is like suddenly flying through syrup instead of air. The Starlink satellites begin to slow. Their precisely calculated orbits start to decay. Each satellite carries a small ion thruster for maintaining altitude, but the thrusters require power, and power comes from solar panels. Solar panels that are being bombarded with radiation. SpaceX engineers watch their telemetry with growing concern. Across the constellation, satellites are reporting anomalies. Some have entered safe mode, shutting down non-essential systems to protect their electronics. Others are struggling to maintain attitude control, tumbling slightly as their sensors are overwhelmed by charged particles. The ground stations are losing contact with individual spacecraft for minutes at a time, as the ionosphere, the electrically charged layer of atmosphere that enables radio communication, churns and roils. The company issues a quiet statement. Service may be degraded for some customers. They do not elaborate on just how degraded, or how close some of their satellites are to becoming very expensive pieces of space debris. Meanwhile, across the American Midwest, farmers are discovering their own crisis. May is planting season. Modern agriculture runs on precision. GPS-guided tractors can plant seeds with accuracy measured in centimeters, maximizing yield from every acre. The GPS constellation, 31 satellites orbiting at roughly 12,500 miles altitude, provides the positioning data that makes this precision possible. Tonight, that data is unreliable. In Iowa, a farmer named Tom watches his tractor's guidance system glitch and reset. The position readings are jumping erratically. Lines that should be perfectly straight are wandering. He tries to recalibrate. The system cannot find enough satellites. The ones it can find are reporting conflicting positions. He is not alone. Across the Corn Belt, farmers are making the same discovery. Some shut down their equipment and wait. Others try to plant anyway, accepting reduced accuracy. A few do not realize the problem until morning, when they discover their neat rows of seeds are anything but neat. The GPS system is not failing exactly. The satellites themselves are fine, orbiting safely above the worst of the storm, but the signals, those satellites broadcast, must travel through the ionosphere to reach receivers on the ground. And tonight, the ionosphere is chaos. Normally, GPS receivers can compensate for ionospheric distortion. They know the typical conditions and can adjust their calculations accordingly. But the storm has scrambled those conditions completely. The ionosphere has developed patches of extreme density, interspersed with regions of unusual thinness. Signals are being bent, delayed, and scattered in ways the correction algorithms cannot handle. Professional surveying equipment, aviation navigation systems, and military applications all use dual-frequency receivers that can largely overcome these problems. But consumer GPS and agricultural guidance systems typically use single-frequency receivers. They are cheaper, and tonight, they are nearly useless. As the night wears on, the storm reaches its peak. At 12:37 a.m. on May 11th, The Goddard Space Weather Center records the moment. The geomagnetic indices spike to their highest values. The storm is officially classified as G5, extreme, the highest rating on the scale. The last time Earth experienced a G5 storm was October of 2003. Power grid operators across North America hold their breath. The 1989 Quebec blackout haunts the industry. On March 13th of that year, a solar storm induced electrical currents in the long transmission lines of Hydro-Quebec. Those currents overwhelmed protective equipment and caused a cascade of failures. 6 million people lost power for 9 hours. The entire province went dark in 90 seconds. Tonight, grid operators have had warning. They have taken precautions. They have reduced power flows in vulnerable lines. They have disconnected certain transformers. They are watching their systems with intense focus, ready to shed load or isolate sections at the first sign of trouble. Geomagnetically induced currents are flowing. The monitors show it clearly. Long transmission lines running east to west, perpendicular to the auroral electrojet, are picking up phantom voltage. In some locations, the readings are concerning, but the grid holds, the preparations work, no major blackouts occur. By dawn on May 11th, the worst of the storm has passed. The magnetosphere begins to recover. The Aurora retreats northward. GPS systems stabilize. Starlink reports normal service. Farmers assess their fields and begin repairs. The world moves on. Within a week, the Ganon storm, as it comes to be called, fades from public consciousness. It becomes a footnote, a curiosity, something that produced beautiful pictures and caused minor inconveniences. But in the space science community, the conversations are very different. They are not talking about what happened. They are talking about what almost happened, and what will happen eventually if we do not prepare. Because the Ganon storm, as powerful as it was nowhere close to the worst the sun can deliver. It was not even particularly unusual by historical standards. It was simply the strongest storm to hit Earth since we became truly dependent on technology in space, and the sun is just getting started. Solar cycle 25, the current 11-year cycle of solar activity, is approaching its maximum. The years 2024 and 2025 represent the peak of the cycle. More active regions, more flares, more coronal mass ejections. The Ganon storm was not an anomaly. It was a preview. Somewhere in the vast nuclear furnace of the sun, magnetic field lines are tangling. Energy is building. Another active region is forming. Another eruption is coming. It might be tomorrow. It might be next month. It might be next year. But it will come. And the satellites we depend on for communication, navigation, weather forecasting, financial transactions, military surveillance, and 1,000 other functions are waiting in orbit. Fragile, exposed, vulnerable. The question is not whether the sun will threaten them again. The question is whether we will be ready when it does. Chapter 2. What is the sun actually doing? To understand the threat, we must understand the source. The sun is not simply a ball of fire hanging in space. It is a thermonuclear reactor of almost incomprehensible scale. A sphere of plasma so massive that it contains 99.8% of all the matter in our solar system. Every planet, every moon, every asteroid and comet combined amounts to a rounding error compared to the sun. At its core, temperatures reach 27 million degrees Fahrenheit. The pressure is so intense that hydrogen atoms are forced together, fusing into helium and releasing energy in the process. Every second, the sun converts roughly 600 million tons of hydrogen into helium. In that same second, it releases energy equivalent to billions of nuclear weapons. This has been happening for 4.5 billion years. It will continue for roughly another 5 billion. The energy generated in the core takes a remarkable journey to reach the surface. It does not travel quickly. The core is so dense, so packed with matter, that photons of light bounce endlessly from atom to atom. A single photon generated in the core today will take somewhere between 10,000 and 170,000 years to reach the surface. The light currently warming your face was born when mammoths still walked the earth. When that energy finally reaches the surface, it enters a very different realm. The visible surface of the sun, called the photosphere, has a temperature of roughly 10,000 degrees Fahrenheit. Hot by earthly standards, but cool compared to the core. Here, the plasma is thin enough that light can finally escape into space, but the photosphere is not calm. It churns and boils with convection currents. Hot plasma rises from below, spreads across the surface, cools slightly, and sinks again. This creates a granular appearance, like the surface of boiling oatmeal magnified to cosmic scale. Each granule is roughly the size of Texas. Above the photosphere lies the chromosphere, a layer of plasma roughly 1,200 miles thick, and above that, extending millions of miles into space, is the corona. The solar atmosphere. Here is where the story gets strange. The corona is hotter than the surface, much hotter. While the photosphere sits at roughly 10,000 degrees, the corona reaches temperatures of 2 million degrees Fahrenheit or more. This seems to violate basic physics. If you walk away from a campfire, you expect to get cooler, not hotter. Yet the sun's atmosphere is hundreds of times hotter than its surface. Scientists have studied this paradox for decades. The current understanding involves magnetic fields. The sun is not merely a ball of hot gas, it is a ball of hot, electrically charged gas. Plasma is profoundly influenced by magnetic fields. The sun's interior is in constant motion. That motion, combined with the electrical nature of plasma, generates powerful magnetic fields. These fields are not stable. They twist and tangle as different parts of the sun rotate at different speeds. The equator completes a rotation in about 25 days. The poles take roughly 35 days. This differential rotation drags magnetic field lines around and around, wrapping them like rubber bands around a ball. The energy stored in these twisted magnetic fields is enormous, and when they become too tangled, too stressed, they release that energy explosively. The plasma in the corona is heated not by radiation from below, but by magnetic energy constantly being dumped into it from these field dynamics. This magnetic activity is not constant. It follows a cycle. In 1610, Galileo Galilei pointed his telescope at the sun and observed dark spots on its surface. Others had noticed sunspots before, but Galileo tracked them carefully. He watched them appear, drift across the solar disk, and disappear. He concluded correctly that the sun was rotating. What Galileo did not know was that the number of sunspots varies in a predictable pattern. In 1843, German astronomer Samuel Heinrich Schwabe published his finding after 17 years of daily observations. Sunspot numbers rise and fall in a cycle averaging roughly 11 years. This solar cycle governs the activity of our star. At solar minimum, the sun may go days or weeks without a single visible sunspot. The corona is relatively calm. Solar storms are rare and generally weak. At solar maximum, the sun may display dozens of active regions. The corona writhes with activity. Storms are frequent and powerful. We are currently in solar cycle 25. It began in December of 2019, when solar minimum was officially declared. The cycle has been climbing toward maximum since then. Predictions initially suggested a relatively mild peak, similar to the modest cycle 24 that preceded it. Those predictions were wrong. Solar cycle 25 has proven significantly more active than expected. By mid-2024, sunspot numbers had exceeded forecast by a substantial margin. The sun was not following the script. It was putting on a show. Sunspots themselves are not the danger, they are symptoms, visible markers of where intense magnetic activity is occurring. A sunspot appears dark only because it is cooler than the surrounding photosphere, roughly 7,000 degrees compared to 10,000. That coolness results from magnetic fields inhibiting convection, preventing hot plasma from rising to the surface. The danger comes from what happens around sunspots. In active regions, magnetic field lines arch above the surface in structures called coronal loops. Plasma flows along these loops, trapped by the magnetic forces. The loops can be stable for days or weeks, but they can also become unstable in moments. When field lines of opposite polarity are forced together, they can reconnect. This is not a gentle process. Magnetic reconnection releases energy with explosive violence. In an instant, the stored magnetic energy converts to kinetic energy, heat, and radiation. The result is a solar flare. Flares are classified by their X-ray output. B-class and C-class flares are minor events, happening constantly during active periods. M-class flares are moderate, capable of causing brief radio blackouts on Earth. X-class flares are the largest, releasing energy equivalent to billions of hydrogen bombs, but an X-class designation is only the beginning. Within the X-class, intensity can vary by a factor of 10 or more. An X1 flare is powerful, An X10 flare is an order of magnitude stronger, and the scale has no upper limit. The largest flares ever recorded have reached X28, and potentially higher. Detectors saturated, the true intensity remains unknown. A solar flare produces electromagnetic radiation across the entire spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, and gamma rays all blast outward at the speed of light. They reach Earth in just over 8 minutes. There is no warning, no time to prepare. The radiation arrives at the same moment we detect the flare occurred. For satellites, this radiation pulse is problematic but manageable. Modern spacecraft are designed to withstand typical radiation environments. They have shielding. Their electronics are hardened against charged particles. A flare might cause temporary glitches or force sensitive instruments offline, but permanent damage from radiation alone is relatively rare. The greater threat comes from what often accompanies a flare, the coronal mass ejection. During major magnetic reconnection events, it is not just energy that is released. Matter is expelled as well. A portion of the corona itself is torn away and hurled into space. Billions of tons of plasma, protons and electrons and heavier ions, all carrying the imprint of the sun's magnetic field, all travelling at tremendous speed. A coronal mass ejection is not the same as a flare, though they often occur together. Flares are bursts of radiation. CMEs are physical objects, clouds of plasma and magnetic field expanding outward from the sun. A flare reaches Earth in 8 minutes. A CME takes 1 to 5 days, depending on its initial velocity. The fastest CMEs travel at over 2,000 miles per second. Even at that speed, they require roughly 18 hours to cross the 93 million miles between the Sun and Earth. This provides warning time. The flare arrives. Satellites detect the particle storm intensifying. Forecasters analyze the data and predict when and whether the CME will hit. Not every CME reaches Earth. The Sun fires them in all directions. Only those launched from regions near the center of the solar disk as viewed from Earth have a good chance of intercepting our planet. Even well-aimed CMEs can curve away due to interactions with the solar wind. Prediction remains an imperfect science. When a CME does strike Earth, the impact occurs in stages. First comes the shock wave. The CME is traveling faster than the ambient solar wind, creating a bow shock like a boat on water. This compressed region of plasma and magnetic field hits Earth's magnetosphere first, suddenly increasing the pressure on our protective bubble. Then comes the sheath region, the turbulent zone just behind the shock. Here the plasma is hot and chaotic, the magnetic field variable and unpredictable. This turbulence can transfer energy into the magnetosphere efficiently, driving geomagnetic activity. Finally comes the magnetic cloud itself, the organized core of the CME. This is where the most intense effects often occur. The magnetic cloud carries its own magnetic field, frozen into the plasma like a fingerprint. The orientation of this field determines how severely the CME will affect Earth. Earth's magnetic field points northward at the equator. If the CME's field also points northward, the interaction is relatively benign. The fields are aligned. They press against each other but do not interconnect. If the CME's field points southward, disaster looms. Southward-oriented fields can connect directly with Earth's northward-pointing field at the magnetopause, the boundary of the magnetosphere. Magnetic reconnection occurs on the day side of Earth. Field lines that were closed, connecting north to south within our magnetosphere, are suddenly opened, connected to the interplanetary magnetic field. The solar wind now has a direct pathway into Earth's magnetic system. Plasma and energy pour in. The magnetosphere is not breached so much as it is opened, and what comes through can wreak havoc. This is what happened in May of 2024. Multiple CMEs with southward-oriented magnetic fields arrived in succession, each one opened. Pathways. Each one pumped energy into the system. The Aurora spread to latitudes that had not seen it in decades. Satellites struggled, GPS faltered, power grids strained, and the sun is not done. Right now, as you listen to these words, active regions are cycling across the solar surface. Magnetic field lines are twisting. Energy is building. The current solar maximum will continue through 2025 and possibly into 2026. More flares are coming. More CMEs are inevitable. Some will miss Earth entirely. Some will deliver glancing blows. But statistically, given the level of activity we're seeing, the probability of another major impact is high. The question is not whether another storm is coming. The question is how severe it will be. And there is another question, one that keeps space scientists and engineers awake at night. The CME that produces the next great storm might not come alone. It might follow on the heels of another eruption, compressing the magnetosphere that has not yet recovered. It might arrive during a period when satellite operators are already dealing with damage from a previous event. It might carry a magnetic field oriented perfectly southward for maximum impact. The Sun does not care about our schedules. It does not care about our satellites. It does not care about the civilization we have built in its light. It simply does what it has always done. It burns, it churns, it explodes, and we have placed $6 billion worth of hardware directly in the path of those explosions. The next chapter in this story is not about the Sun. It is about what we have put in orbit around Earth, the satellites that govern modern life, the fragile machines that could be swept from the sky by forces we cannot control. They are more vulnerable than you imagine. Chapter 3. The Ganon Storm of 2024. They named it after a scientist. Jennifer Ganon had spent her career studying geomagnetic storms, developing models to predict how Earth's magnetic field would respond to solar impacts. On May 10th, 2024, one of the most powerful storms in decades arrived to test everything she and her colleagues understood. The scientific community would eventually honor her work by attaching her name to the event. The Ganon storm did not announce itself dramatically. No single apocalyptic moment, no sudden catastrophe visible to the naked eye. It arrived as a series of impacts, waves of charged particles and magnetic disturbance washing over Earth in succession, each one compounding the effects of those before. At the Space Weather Prediction Center in Boulder, Colorado, forecasters had been tracking the threat for days. Active Region 3664 had emerged on the Sun's eastern limb on May 1st, 2024. By May 3rd, it had grown to roughly 17 times the diameter of Earth. This was a monster sunspot group, one of the largest of solar cycle 25. Between May 8th and May 9th, the active region erupted repeatedly. Forecasters counted at least 7 significant coronal mass ejections launched toward Earth in less than 48 hours. This was unusual. CMEs typically occur in isolation, allowing Earth and its magnetosphere time to recover between impacts. This bombardment would be different. The first CME arrived on May 10th at roughly 12:30 p.m. Eastern Time. Its initial impact was strong but manageable. The magnetosphere compressed but held. Geomagnetic indices began to climb. Forecasters upgraded their predictions. This would be a significant storm. Then the second CME arrived, and the third. Each impact came before the magnetosphere had fully recovered from the previous one. The cumulative effect was severe. By evening, the storm had reached G4 classification. Severe. One step below the maximum rating, and then it got worse. Overnight on May 10th into May 11th, the 4th and 5th CMEs struck in rapid succession. The magnetic fields they carried were oriented strongly southward. They connected efficiently with Earth's field. Energy poured into the magnetosphere. The Aurora exploded southward. At 12:37 a.m. on May 11th, the storm peaked at G5. Extreme. This was the first G5 storm since the Halloween storms of October 2023. Only a handful of such events had occurred since modern measurement began. What did G5 actually mean on the ground? The scale is somewhat abstract, based on geomagnetic indices that measure how much Earth's magnetic field is being disturbed, but the effects were concrete and widespread. Start with the Aurora. Under normal conditions, the Aurora borealis is visible in a ring around the magnetic North Pole, roughly corresponding to latitudes above 60 degrees. During moderate storms, that ring expands southward to perhaps 50 degrees latitude. Southern Canada, the northern tier of American states during the Ganon storm, Aurora was photographed as far south as Puerto Rico, latitude 18 degrees. People in Jamaica saw colors in the northern sky. Observers in central Mexico witnessed the lights. This was an aurora visible across nearly the entire northern hemisphere. The expansion occurred because charged particles normally deflected by the magnetosphere were being funneled deep into the atmosphere along magnetic field lines. The further south the aurora reached, the more particles were penetrating the system. Those same particles were causing problems far above the visible display. In low Earth orbit, the atmosphere was swelling. Solar radiation and charged particles were heating the thermosphere, the layer between roughly 50 and 400 miles altitude. As gas heats, it expands. The result was a significant increase in atmospheric density at orbital altitudes where thousands of satellites fly. For satellites in stable orbits, this was an immediate problem. More atmospheric density means more drag. More drag means faster orbital decay. Satellites that would normally maintain their altitude for months or years were suddenly falling faster than predicted. SpaceX operates the largest satellite constellation in history. Starlink, designed to provide global internet coverage, had deployed more than 5,000 satellites by May of 2024. To most orbit between 200 and 300 miles altitude. This is low by historical standards, chosen deliberately to reduce communication latency. But it also places the satellites directly in the region most affected by atmospheric expansion during storms. SpaceX engineers watched their telemetry with concern. Across the constellation, satellites were being dragged downward faster than their onboard thrusters could compensate. The company had experienced this before. In February of 2022, a much smaller storm had caught 40 newly launched Starlink satellites in an expanded atmosphere. Unable to raise their orbits fast enough, most of them re-entered and burned up. Nearly $40 million in hardware destroyed by a minor storm. The Ganon storm was far more powerful than that 2022 event. If it continued at peak intensity for days, the entire Starlink constellation could be at risk. Satellites would be dragged down faster than they could be replaced. Coverage would degrade. Customers would lose service. Fortunately, the storm began to subside by May 12th. The atmosphere would take weeks to return to normal density, but the worst was over. Starlink survived. But the close call highlighted a fundamental vulnerability. These satellites exist in a narrow zone where they are low enough to provide fast internet but high enough to stay in orbit. Solar storms directly attack that balance. GPS faced different problems. The constellation orbits much higher, roughly 12,500 miles altitude, largely above the affected atmospheric layers. But GPS signals must travel through the atmosphere to reach ground receivers. And the ionosphere, the layer between roughly 50 and 400 miles altitude where the atmosphere is electrically charged, was in chaos. Normally, GPS receivers apply corrections to account for ionospheric delay. The charged particles in the ionosphere slow radio signals slightly, and this delay must be factored into position calculations. Under normal conditions, the ionosphere is relatively predictable. Models work well, corrections are accurate. During the Ganon storm, the ionosphere developed extreme gradients and irregularities. Patches of very high electron density formed adjacent to regions of unusual depletion. The boundaries between these patches were sharp and unpredictable. GPS signals passing through experienced wildly varying delays that changed from moment to moment. Single-frequency receivers, the type found in most smartphones and consumer devices, were essentially unusable for precision applications. Position errors of tens of meters were common. In some locations, receivers could not obtain a valid position at all. Dual-frequency receivers, used by surveyors and aviation, performed better but still experienced degradation. The Federal Aviation Administration issued advisories. Pilots were warned of potential GPS unreliability. For farmers in the Midwest, the timing could not have been worse. May is planting season. Modern precision agriculture relies heavily on GPS guidance systems to plant seeds in optimal patterns, applying fertilizer and pesticide exactly where needed. Many farmers use auto-steer systems that drive tractors autonomously along pre-programmed paths. These systems require centimetre-level accuracy. During the Ganon storm, that accuracy vanished. Farmers reported their tractors wandering off course. Rows that should have been straight curved erratically. Some farmers stopped planting entirely, waiting for conditions to improve. Others pressed on, accepting reduced precision. The economic impact across the agricultural sector was difficult to quantify, but certainly reached into the millions of dollars. Aviation faced disruption as well. High-frequency radio communications used for transoceanic flights beyond the range of ground-based radar experienced blackouts during the strongest periods of the storm. Airlines were forced to reroute some polar flights to avoid both communication gaps and increased radiation exposure at high latitudes. When a solar storm drives particles deep into the atmosphere, radiation levels increase significantly at aircraft cruising altitudes. During the Ganon storm, some flight crews received radiation doses equivalent to several chest X-rays during single flights. Aviation authorities track cumulative exposure for flight crews, and events like this add measurably to lifetime totals. Power grids, the infrastructure that triggered the most concern among forecasters, largely weathered the storm. The 1989 Quebec blackout remains the most dramatic example of what solar storms can do to electrical infrastructure. That storm induced currents in long transmission lines, overloaded transformers, and collapsed the Hydro-Quebec system in 90 seconds. Modern grid operators have learned from that event. They monitor geomagnetically induced currents in real time. They have procedures for reducing power flows in vulnerable lines. They can disconnect certain transformers proactively. During the Ganon storm, operators across North America implemented protective measures. Some transmission capacity was reduced. Some transformers were isolated. The costs of these precautions were substantial. Electricity that would normally flow through optimal paths had to be rerouted. Generation that would normally be dispatched had to be held back, but no major blackouts occurred. The grid survived because operators had warning and took action. The forecasts from Boulder provided roughly 18 hours of lead time before each CME impact. That was enough to prepare. Barely. What if the warning had been shorter? What if a faster CME had arrived with only 6 hours' notice? What if multiple storms had hit in rapid succession without time to implement protective measures between them? These questions haunted the power industry in the weeks following the Ganon storm. The grid held this time. Would it hold next time? The aftermath revealed how close the modern world came to significant disruption. Satellite operators reported anomalies across their fleets. Communication satellites experienced interference and required corrective maneuvers. Earth observation satellites lost data during the peak of the storm. Scientific satellites designed to study the space environment were themselves affected by the environment they were studying. The economic impact was real but diffuse. No single catastrophic failure made headlines. Instead, thousands of small degradations accumulated. Farmers with ruined planting, airlines with rerouted flights, satellite operators with increased fuel consumption, and shortened spacecraft lifespans. GPS users with lost productivity. A more complete accounting would take months or years. Insurance claims would be filed. Lawsuits might follow. The full cost of the Ganon storm might never be precisely known. What was known immediately was that the forecasts had been accurate. The Space Weather Prediction Center had provided timely warnings. Satellite operators had received advance notice. Grid operators had prepared. The system worked as designed. But the system was designed for storms like this one. Powerful but not unprecedented. Damaging but not catastrophic. A G5 storm is the top of the scale, but that scale was created by humans, based on the storms humans have observed in the modern era. There is no G6. Not because stronger storms are impossible, but because the scale simply does not go higher. History tells us that storms far more powerful than the Ganon event have struck Earth in the past, not in the age of satellites, not in the age of power grids, but they happened, and they will happen again. The Ganon storm was a warning shot, a reminder that the sun is not a stable and predictable neighbor. It is a dynamic and occasionally violent star that humans have grown dangerously dependent upon ignoring. The satellites in orbit cannot be so complacent. They exist at the mercy of the space environment, and that environment just demonstrated exactly how merciless it can become. The next chapter examines those satellites in detail, where they are, what they do, and why they are far more vulnerable than most people realize. Chapter 4. Our satellites are more vulnerable than you think. Look up at night. The sky appears empty save for stars and the occasional airplane, but that emptiness is an illusion. Orbiting above you right now are more than 7,000 active satellites. They form an invisible infrastructure that modern civilization has grown utterly dependent upon without most people ever thinking about it. Your phone finds your location through GPS. Your weather forecast comes from satellite imagery. The package you ordered will be tracked by satellite as it crosses the ocean. The television news shows footage relayed through satellites. The financial transaction you made this morning was time-stamped by satellite atomic clocks. The military forces that protect your country depend on satellite surveillance, satellite communication, and satellite navigation for virtually every operation. 50 years ago, none of this was true. Satellites were expensive curiosities, scientific instruments and communication relays used by governments and large corporations. Today they are essential infrastructure, as critical to daily life as roads and power lines. And we have built this dependency with remarkable speed, with almost no public discussion and with inadequate appreciation for the vulnerabilities involved. Start with the numbers. In 1970, roughly 300 active satellites orbited Earth. By 2000, the count had reached roughly 600. Then came the mega constellation era. SpaceX began launching Starlink in 2019. Other companies followed. By 2024, more than 7,000 active satellites were in orbit. More than half had been launched in the previous 5 years. This is not simply growth, it is exponential expansion. The orbital environment is being transformed within a single decade, and the rate is accelerating. Plans call for tens of thousands of additional satellites in the coming years. OneWeb, Amazon's Project Kuiper, Chinese and European constellations. Within a decade, there could be 50,000 or more active satellites overhead. Each satellite represents a technological marvel. Consider a Starlink satellite. It masses roughly 260 kilograms. It carries phased array antennas that can simultaneously connect with hundreds of ground terminals and with other satellites via laser crosslinks. It has solar panels for power, batteries for eclipse periods, and an ion thruster for maintaining altitude and eventually deorbiting at end of life. It communicates with ground control, processes traffic data, and maintains attitude control using reaction wheels and star trackers. All of this fits in a package roughly the size of a table. It costs perhaps $250,000 to build. It must function autonomously in the harsh environment of space for 5 to 7 years, with no possibility of repair. Space is not empty. It is filled with hazards that would destroy unprotected electronics in hours. The first hazard is radiation. Earth's magnetosphere shields the surface from most cosmic rays and solar particles. But satellites orbit outside much of that protection. They are bathed in radiation constantly. Solar. Panels degrade as energetic particles damage the semiconductor material. Electronics accumulate radiation dose that can cause bit flips, latch-up events, and gradual performance degradation. Satellite designers account for radiation. They use hardened components. They implement error correction in software. They design circuits to be tolerant of single-event upsets. But there are limits. More radiation hardening means more mass, more cost, more power consumption. Commercial satellites are designed to survive the typical radiation environment, with margin for occasional storms. They are not designed for the worst the sun can deliver. The second hazard is thermal cycling. A satellite in low Earth orbit circles the planet roughly every 90 minutes. For half that orbit, it is in sunlight. For the other half, it is in Earth's shadow. The temperature swing can exceed 300 degrees Fahrenheit. Materials expand and contract. Joints flex. Connections loosen over thousands of cycles. Thermal stress is a leading cause of satellite failure. The third hazard is atomic oxygen. In low Earth orbit, the upper atmosphere contains significant amounts of oxygen in atomic form. These atoms are highly reactive. They erode exposed surfaces through chemical sputtering. Protective coatings are essential, but even coatings wear away over time. The fourth hazard is debris. More than 36,000 tracked objects larger than 10 centimeters are in orbit. Millions of smaller fragments are untracked. Even a paint chip traveling at orbital velocity carries the kinetic energy of a bullet. A collision with debris larger than a centimeter could disable a satellite. A collision with debris larger than 10 centimeters could destroy it entirely. And now add solar storms to this list of hazards. When a coronal mass ejection hits Earth, it does not simply rattle the magnetosphere and create pretty auroras. It directly affects every satellite in orbit through multiple mechanisms. The first mechanism is atmospheric drag. Solar heating expands the thermosphere, increasing atmospheric density at orbital altitudes. For satellites in low Earth orbit, this is immediate and dangerous. Their orbits decay faster. They must burn fuel to maintain altitude. If a storm is severe enough or long enough, satellites can be dragged down faster than their propulsion systems can compensate. SpaceX learned this lesson in February of 2022. A minor geomagnetic storm expanded the atmosphere just as 49 newly launched Starlink satellites were in their initial orbit-raising phase. The satellites were low and slow, not yet in their operational orbits. The increased drag was overwhelming. Despite onboard thrusters firing continuously, most of the satellites could not overcome the drag. They re-entered the atmosphere and burned up. Nearly $40 million in hardware was lost to a storm that barely registered on geomagnetic indices. The Ganon storm was far more severe. Had it arrived while a fresh batch of Starlink satellites was in orbit raising, the loss could have been worse. Had the storm lasted longer or been more intense, even operational satellites at higher altitudes could have been threatened. The second mechanism is radiation damage. During a solar storm, the particle environment intensifies dramatically. Protons accelerated by shock waves ahead of coronal mass ejections can damage solar cells and sensitive electronics. X-rays from associated flares can deposit charge in unintended locations. Satellites experience a compressed lifetime of radiation exposure in a matter of hours. Operators respond by putting satellites into safe mode. They power down non-essential systems. They orient spacecraft to minimize exposed area. They pause science observations and data collection. But safe mode is not a perfect shield. Damage accumulates regardless. Every major storm shortens the operational life of every satellite it touches. The third mechanism is charging. In the disturbed space environment during a storm, satellites can accumulate electrical charge. The plasma environment becomes highly variable. Different parts of a satellite charge to different potentials. Eventually, the voltage differential becomes large enough to cause an electrostatic discharge. An arc of electricity across the spacecraft structure. Discharges can destroy sensitive circuits. They can upset attitude control systems. They can corrupt memory. They can trigger cascading failures that end missions entirely. The Van Allen radiation belts, which intensify during storms, are particularly dangerous for satellites in medium Earth orbit, where GPS and similar constellations reside. The fourth mechanism is communication disruption. Satellites must communicate with ground stations and with each other. Radio signals travel through the ionosphere, which becomes severely disturbed during geomagnetic storms. Signal quality degrades, data rates must be reduced. Links may be lost entirely during peak disturbance. For autonomous satellites designed to operate with minimal ground contact, communication blackouts are manageable. For constellations that require constant coordination, blackouts create operational chaos. For human spaceflight, the inability to communicate with crew can create life-threatening situations. Now consider the cumulative effect. 7,000 satellites, each exposed to these hazards, each designed with finite margin. A severe solar storm hits. Some satellites enter safe mode, others lose contact. A few experience immediate failures. Many accumulate damage that will shorten their remaining lives. The storm passes. Operators assess the damage. Most satellites recover, but some do not. They drift out of control. They become debris. And here is where the math becomes terrifying. Low Earth orbit is increasingly crowded. Satellites operate in precisely calculated orbital planes, their paths, choreographed to avoid collision. Ground tracking systems monitor every object and predict close approaches. When two objects are projected to come dangerously close, one must maneuver. This system works when operators know where their satellites are, when communication links are functioning, and when thrusters respond to commands. During a solar storm, all three conditions may be compromised. Satellites experience drag differently depending on their size, shape, and altitude. Their orbits change unpredictably. The atmosphere is not uniform. It develops bulges and irregularities. Tracking becomes less accurate just as the environment becomes more dangerous. At the same time, communication may be degraded or impossible. Operators cannot send commands. Satellites cannot report their status. The coordination that normally prevents collisions breaks down. If two satellites collide, they do not simply bounce off each other. Orbital velocity is roughly 17,500 miles per hour in low Earth orbit. A collision at that speed is catastrophic. Both spacecraft are destroyed instantly, fragmented into thousands of pieces. Each piece becomes a new debris object, traveling at orbital velocity, capable of destroying another satellite. A single collision could initiate a cascade. More debris means more collision probability. More collisions mean more debris. The process could feed on itself, consuming satellites faster than they can be replaced, generating debris faster than it can be tracked or avoided. This nightmare scenario has a name. Scientists call it the Kessler Syndrome, and a severe solar storm could be the trigger that sets it in motion. The satellites we depend on are not permanent fixtures. They are temporary machines, exposed and vulnerable, orbiting in an environment we do not fully understand and cannot fully predict. A single, severe storm could blind dozens or hundreds of them. A truly extreme storm could trigger a debris cascade that closes orbital shells for generations. We have built our civilization on these machines without building adequate backup systems. We have placed our faith in them without understanding their fragility. And we have done so just as the Sun enters its most active period in decades. The question is no longer whether satellites will fail. The question is how many, how fast, and whether we can recover when they do. The next chapter explores the Kessler Syndrome in detail, what it is, how it could happen, and why it might be the greatest technological catastrophe humanity has ever faced. Chapter 5. The Kessler Nightmare. In 1978, Donald Kessler was a NASA scientist working on an obscure problem. He was studying meteoroids, the tiny natural particles that occasionally strike spacecraft. But as he analyzed orbital data, he noticed something troubling. The number of artificial objects in orbit was growing, and the more objects there were, the more likely they were to collide. Kessler developed a mathematical model. His equations described a tipping point. Below a certain density of objects, collisions would be rare. The debris they generated would gradually re-enter the atmosphere and burn up. The system would be stable. But above that density, something different would happen. Collisions would create debris faster than it could naturally clear. Each collision would increase the probability of the next. A cascade would begin. His 1978 paper introduced what would come to be called the Kessler Syndrome. At the time, it was a theoretical concern. There were only a few thousand objects in orbit. The threshold he described seemed far in the future. 46 years later, the future has arrived. Today there are more than 36,000 tracked objects in orbit. That number includes approximately 7,000 active satellites, but also more than 23,000 pieces of debris, spent rocket stages, dead satellites, fragments from explosions and collisions, and those are only the pieces large enough to track, roughly 10 centimeters or larger. Below the tracking threshold, the situation is far worse. Estimates suggest there are approximately 1 million objects larger than 1 centimeter orbiting Earth, 100 million objects larger than 1 millimeter. These smaller fragments are invisible to ground-based radar. But they are no less dangerous. At orbital velocity, a paint fleck has the kinetic energy of a rifle bullet. A marble-sized fragment hits like a grenade. A piece the size of a baseball carries the force of a car crash. Even small debris can destroy a spacecraft or create more debris through secondary impacts. The math is relentless. More objects mean more collision probability. More collisions mean more objects. The debris from a single collision can number in the thousands. Each new piece follows its own orbital path, crossing other orbits, creating new opportunities for impact. Kessler's cascade has not yet begun in earnest, but the precursors are visible. In 2007, China tested an anti-satellite weapon by destroying one of its own defunct weather satellites. The target was in a crowded region of low Earth orbit, roughly 850 kilometers altitude. The weapon struck at relative velocity. The satellite fragmented into more than 3,500 trackable pieces and likely hundreds of thousands of smaller fragments. In a single moment, China increased the debris population in that orbital shell by roughly 25%. Those fragments will remain in orbit for decades. They cross the paths of thousands of other objects. They have already caused numerous close approaches requiring satellite operators to execute collision avoidance maneuvers. In 2009, an operating Iridium communication satellite collided with a defunct Russian Cosmos satellite. Neither operator had maneuvered to avoid the collision. The tracking data had shown a close approach, but close approaches happen constantly. Resources for avoidance maneuvers are limited. The probability assessment suggested low risk. The assessment was wrong. The collision generated roughly 2,000 trackable fragments. Unlike a deliberate test, this was an unintentional demonstration of what the Kessler Syndrome looks like at small scale. 2 objects, 1 collision, 2,000 new hazards. These fragments join the 23,000 other pieces of debris already being tracked. They spread along their orbital paths, diffusing into expanding clouds. They cross other orbits. They threaten other satellites. Each one is a potential seed for further collisions. And now consider what a solar storm adds to this equation. During the Ganon storm, atmospheric drag increased significantly at low Earth orbit altitudes. Satellites experienced accelerated orbital decay. Their positions became harder to predict as the atmosphere developed irregular bulges and variations. The precision tracking that enables collision avoidance degraded just as the collision risk increased. At the same time, communication with satellites became unreliable. Operators could not send maneuvering commands, satellites could not report their status. Automated conjunction warnings piled up faster than ground teams could process them. If a collision had occurred during the Ganon storm, the results could have been catastrophic beyond the immediate destruction. Debris would have been generated in an environment where tracking was compromised and communication was impaired. Additional collisions could have followed before anyone understood what was happening. The cascade could have begun. It did not happen in May of 2024. We were lucky. But luck is not a strategy. The physics of the Kessler Syndrome are inexorable once triggered. A single collision generates debris. That debris spreads. The probability of the next collision increases. Another collision occurs, more debris, higher probability, faster collisions, exponential growth. Computer models have simulated these cascades. The results are sobering. In the worst-case scenarios, entire orbital shells become unusable within years. The debris density reaches levels where any satellite launched into that region has a near certainty of being struck, not immediately, not dramatically, but inevitably. Low Earth orbit, where the space station flies, where Earth observation satellites operate, where communication constellations like Starlink reside, could become a shooting gallery. Every orbit would be a gauntlet. Every satellite would be temporary. Medium Earth orbit, home to GPS and similar navigation systems, is less crowded but not immune. Debris generated in lower orbits can reach higher regions through collision-induced velocity changes. The cascade could spread upward. Geostationary orbit, the precious ring 35,000 kilometers, above the equator where communication and weather satellites maintain fixed positions relative to Earth, would be affected last. But it would be affected. The global infrastructure we have placed in the sky would be consumed piece by piece by its own wreckage. Recovery from a full Kessler cascade is not measured in years. It is measured in centuries. Objects in high orbits decay very slowly. At geostationary altitude, there is essentially no atmospheric drag. Debris placed there will orbit for thousands of years. Even in low Earth orbit, debris at 800 kilometers altitude will remain for decades before re-entering. Active debris removal is theoretically possible. Concepts exist for spacecraft that could rendezvous with debris and deorbit it. But the scale of the problem defies such solutions. Removing 36,000 objects one at a time, assuming each removal mission costs millions of dollars and takes months to execute, would require resources beyond any nation's willingness to spend. And that is the current debris population. After a cascade, the number could be vastly higher. Humanity could be locked out of space for generations, not by enemy action, not by deliberate choice, but by the accumulated consequences of our own activity, triggered by a solar storm we could not prevent. This is not science fiction. This is orbital mechanics. The equations do not care about our intentions or our needs. They simply describe what happens when objects collide at hypersonic velocity in a shared environment. The connection between solar storms and the Kessler Syndrome is underappreciated. Most discussions of space debris focus on steady accumulation over time. Satellites fail. Upper stages are abandoned. Accidental collisions occur. The debris population grows gradually. Solar storms inject chaos into this gradual process. They disrupt tracking. They impair communication. They create conditions where the careful coordination that prevents collisions breaks down. They can also directly destroy satellites, creating sudden influxes of debris. If a severe storm caused multiple satellite failures simultaneously, the resulting debris could initiate collisions that would not otherwise have occurred. Each collision would add to the debris environment. The cascade would have begun not from a single dramatic impact, but from distributed failures across a constellation. The mega-constellation era makes this scenario more likely. Starlink alone has more than 5,000 satellites in closely coordinated orbital shells. These satellites maintain precise spacing through continuous communication and periodic maneuvers. They fly in planes that frequently cross other planes. They depend on automation to avoid collisions with each other and with debris, disrupt that automation during a solar storm, impair communication, cause navigation failures, induce uncontrolled tumbling in even a fraction of the constellation, The collision probability rises dramatically. SpaceX engineers are aware of this risk. They design their satellites for survivability. They maintain operational protocols for storms. They have escape routes and safe modes and contingency plans. But no plan survives contact with the enemy. And the Sun is an adversary that does not follow human rules. The nightmare scenario is not the most probable outcome. Most solar storms cause manageable disruption. Most satellites survive. The orbital environment degrades gradually rather than catastrophically. The cascade does not begin. But the nightmare scenario is possible, and as the orbital environment grows more crowded, as solar activity increases toward maximum, as more constellations join Starlink in the orbital commons, the probability creeps upward. Donald Kessler is retired now. He watches the proliferation of satellites with concern. He has been warning about this outcome for almost half a century. For most of that time, few listened. The problem seemed distant. The sky seemed empty. The sky is not empty anymore. It is filling with machines at an unprecedented rate. And the Sun is building toward maximum activity at precisely the moment when those machines are most numerous and most vulnerable. Kessler hoped his syndrome would remain theoretical. He hoped humanity would manage the orbital environment wisely. He hoped we would not trigger the cascade. We have not yet proven him wrong, but we have not proven him right either. The test is coming. A storm is building. The satellites are waiting. What happens next depends on forces beyond our control, but to understand how serious this threat truly is, we must look backward before we look forward. Solar storms are not new. The most powerful one ever recorded struck Earth more than a century and a half ago. It was called the Carrington event, and if it happened today, it would change everything. Chapter 6. The Carrington event and what it taught us. September 1st, 1850. 9. A Thursday morning in England. Richard Carrington is in his private observatory, a small building on the grounds of his estate in Red Hill, Surrey. He is wealthy, an amateur astronomer of considerable skill, and he has dedicated himself to studying the sun. His method is meticulous. He projects the solar image through his telescope onto a screen and carefully sketches the sunspots he observes. Day after day, year after year, he documents the blemishes on the sun's face. It is tedious work. It is important work. It is about to make him famous. At 11:18 in the morning, Carrington notices something unusual. 2 brilliant patches of white light have appeared among the sunspots he is sketching. They are intensely bright, brighter than the surrounding solar surface. They are also moving, drifting across the sunspot group, even as he watches. Carrington is startled. He has never seen anything like this. He rushes from the observatory to find a witness, but by the time he returns 5 minutes later, the bright patches have faded. The event lasted only 5 minutes, but Carrington has observed something no human had ever documented before: a white light solar flare. He does not know what it means. He notes the observation carefully. He sketches the position of the flare relative to the sunspots. He records the time. Then he returns to his regular work. 17 hours later, the consequences arrive. In the early morning hours of September 2nd, the sky begins to glow. Not just in the polar regions where auroras are common, everywhere. Across North America, the Aurora borealis blazes with colours never seen at such latitudes. Red and green and purple curtains of light reach from horizon to horizon. The display is so bright that people wake from sleep convinced their towns are on fire. In the Rocky Mountains, gold miners emerge from their tents at 1 in the morning and begin making breakfast, believing dawn has arrived. In the northeastern United States, the light is bright enough to read a newspaper at midnight. Ships at sea record auroras as far south as the Caribbean. In the southern hemisphere, the Aurora australis reaches into Colombia and Queensland. The light is beautiful. The light is also terrifying. Some observers believe they are witnessing divine judgment. Churches fill with people praying for deliverance. Others simply stand in wonder, watching the heavens perform. But the aurora is only the visible symptom. The invisible effects are already causing chaos. The telegraph was the internet of 1859. Lines stretched across continents, connecting cities and nations, carrying news and commerce at the speed of electricity. For the first time in human history, information could travel faster than a horse or a ship. The telegraph had transformed business, journalism, and government. The world had grown dependent on those thin copper wires. On the morning of September 2nd, the telegraph system went mad. Operators reported sparks leaping from their equipment. In some offices, telegraph paper caught fire. Operators received shocks when they touched their keys. Lines that had functioned perfectly for years suddenly carried wild currents that no operator had sent. In Pittsburgh, the telegraph office reported flames shooting from the circuits. In Washington, an operator described a continuous stream of fire from the key to the wire. In Philadelphia, operators disconnected their batteries entirely, fearing explosion, yet found that messages continued to flow. The auroral currents in the atmosphere were strong enough to power the telegraph without any human-generated electricity. The disruption lasted for days. Some lines were damaged beyond immediate repair. Communications between cities was sporadic at best. The carefully constructed network that had connected the world was reduced to unreliable fragments. For Carrington and other scientists, the coincidence was striking. A massive solar flare observed on September 1st. A global aurora and electromagnetic chaos on September 2nd. The connection seemed obvious. The Sun had somehow reached across 93 million miles of space and touched the Earth. Carrington was cautious in his conclusions. He noted the correlation but hesitated to claim causation. One event following another does not prove the first caused the second. But as reports accumulated from around the world, the pattern became undeniable. The Sun had attacked the Earth with invisible force, and the Earth's technology had suffered. The Carrington event, as it came to be called, was the most powerful geomagnetic storm in recorded history. Modern analysis of ice cores, tree rings, and other proxy records suggests it may have been a once-in-500-year event, perhaps rarer. The energy involved was staggering. Scientists now understand what happened. The solar flare Carrington observed was accompanied by a massive coronal mass ejection. The CME was both extremely fast and extremely powerful. It crossed the distance from Sun to Earth in approximately 17 hours, a transit time that implies a velocity of over 2,000 kilometers per second. Most CMEs take 2 to 4 days. The CME also carried a strongly southward-oriented magnetic field. This allowed it to couple efficiently with Earth's magnetosphere, transferring energy with maximum effectiveness. The combination of speed, power, and magnetic orientation made the Carrington event a perfect storm. The geomagnetic disturbance was intense beyond anything measured since. Modern indices did not exist in 1859, but scientists have estimated the equivalent values from historical records. The DEST index, which measures the global magnetic disturbance, likely reached negative 1600 or lower. For comparison, the Ganon storm of 2024 reached approximately negative 400. The Carrington event was 4 times stronger. The auroras reached latitudes that had never seen them and have not seen them since. The electromagnetic induction effects were powerful enough to operate telegraph equipment without batteries. The storm was not merely severe, it was exceptional, and it happened at a time when humanity's technological infrastructure was primitive by modern standards. The telegraph was essentially the only electrically based technology in existence. There were no power grids, no radio systems, no satellites, no computers. The damage was significant, but contained. What would happen if a Carrington-class event struck today? This question has haunted scientists and engineers for decades. The answer is deeply troubling. Modern civilization runs on electricity. The power grid is the foundation of everything else. Without electricity, there is no water pressure in most municipal systems, no fuel pumping at gas stations, no refrigeration for food or medicine, no communication networks, no computing, no financial transactions, no traffic lights, no modern medical care. The list is endless. A Carrington-class event would induce enormous currents in long-distance power transmission lines. These geomagnetically induced currents would flow through transformers, heating their cores beyond design limits. Transformers are the critical nodes of the power grid. They step voltage up for efficient long-distance transmission and step it down for local distribution. They are custom-built, expensive, and time-consuming to manufacture. The world does not maintain large inventories of spare transformers. Studies have estimated that a Carrington-class event could damage or destroy hundreds of high-voltage transformers across North America alone. Similar effects would occur in Europe, Asia, and everywhere else with extensive power grids. The damage would not be uniform. Some regions would be hit harder than others depending on the orientation of their transmission lines and the local geology. But the overall impact would be severe. Replacing a single large transformer takes months under normal conditions. The specialized factories that build them have limited capacity. After a Carrington event, demand would spike globally, while production facilities might themselves be without power. The wait for replacement transformers could extend to years. During that wait, large portions of the affected continents would be without electricity, not for hours or days, for months or years. The cascading consequences are difficult to fully imagine. The economic estimates vary widely. A 2013 study by Lloyd's of London and the Atmospheric and Environmental Research Company estimated that a Carrington-class event could cause between $0.6 and $2.6 trillion in damage to the United States alone. Other studies have produced even higher figures. The uncertainty reflects the genuine difficulty of predicting how modern systems would fail under unprecedented stress. Satellites would face even more direct assault. The Carrington event predated the space age by a century. No human technology was in orbit to experience its effects. But we can extrapolate from what we know about lesser storms. The radiation environment during a Carrington-class event would be extreme. Solar energetic particles accelerated by the CME shockwave would penetrate deep into the inner magnetosphere. Satellites in all orbital regimes would be exposed to doses far exceeding their design specifications. Many would fail immediately. Others would suffer permanent damage, shortening their operational lives to months or weeks. The atmospheric expansion at low Earth orbit would be dramatic. Satellites that normally experience minimal drag would suddenly be ploughing through an atmosphere 10 or 20 times denser than normal. Small satellites with limited propulsion capability would be swept from the sky. Even larger satellites would struggle to maintain altitude, GPS, would degrade or fail. Communication satellites would go silent. Weather satellites would stop reporting. The eyes and ears humanity has placed in orbit would be blinded and deafened in a matter of hours. Recovery would be measured in years. Launching replacement satellites requires functioning rockets, functioning ground infrastructure, and functioning economies. All of those would be compromised by the terrestrial effects of the same storm. The space age could effectively end, at least temporarily, from a single solar eruption. This is not speculation. This is physics. The Sun is capable of producing events far more powerful than anything witnessed in the modern era. The Carrington event proves this, and it was probably not even the strongest storm the Sun can generate. Analysis of carbon-14 in tree rings has revealed evidence of even more powerful events in the historical record. In 774 and 993 AD, spikes in carbon-14 suggest solar storms that may have been 10 times more powerful than the Carrington event. These occurred before any written records of their effects, but the isotopic evidence is clear. The Sun occasionally produces monsters. The probability of a Carrington-class event in any given year is estimated at roughly 1 to 2%. Over a decade, that compounds to 10 to 20%. Over a human lifetime, it approaches certainty. The question is not whether another Carrington event will occur. The question is when. We have been lucky. The space age has coincided with a period of relatively moderate solar activity. The largest storms of the past 60 years have been severe but not catastrophic. The Ganon storm of 2024 was the strongest in 2 decades, but it was still far below Carrington levels. That luck will not last forever. Somewhere in the statistical distribution of solar activity, a Carrington-class event is waiting. It might arrive during the current solar maximum. It might arrive decades from now. But it will arrive. When it does, it will find a world utterly unprepared. A world that has built its civilization on invisible infrastructure in the sky. A world that has forgotten the sun can rage. The next chapter examines exactly how solar storms attack our technology, the mechanisms of destruction, the pathways of failure, the specific vulnerabilities we have created and continue to create. Understanding the enemy is the first step towards survival. Chapter 7. How solar storms attack technology. The sun does not send soldiers. It does not deploy weapons in any conventional sense. Yet it attacks our technology through multiple mechanisms, each exploiting different vulnerabilities, each capable of causing damage that ranges from annoying to catastrophic. Understanding these mechanisms is essential to understanding the threat. The first mechanism is the electromagnetic radiation. When a solar flare erupts, it releases energy across the entire electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays and gamma rays all blast outward at the speed of light. They reach Earth in 8 minutes and 19 seconds. There is no warning. The radiation arrives at the same instant we detect that the flare occurred. For satellites, this radiation pulse creates immediate problems. X-rays and extreme ultraviolet light are absorbed by the upper atmosphere, heating it rapidly. The thermosphere expands within minutes, increasing drag on low-orbiting satellites before operators have any chance to react. The first sign of a major flare may be telemetry showing unexpected orbital decay. The radiation also affects satellite electronics directly. High-energy photons can penetrate shielding and deposit charge in semiconductor devices. This can cause single-event upsets, bit flips in memory that corrupt data or trigger unexpected behavior. More severe events can cause latch-up, a condition where a circuit locks into a state that draws excessive current and can destroy the component. Solar cells are particularly vulnerable. The photovoltaic materials that convert sunlight to electricity degrade when bombarded with high-energy radiation. Each major flare shortens the operational life of every solar panel it strikes. Satellites are designed with margin to account for this degradation, but that margin is finite. Radio communication suffers immediately. The same X-rays that heat the upper atmosphere also ionize it, dramatically increasing the electron density in the lower ionosphere. High-frequency radio waves, the kind used for long-distance communication and aviation, are absorbed by this enhanced ionization. Radio blackouts can last for hours, affecting everything from amateur radio operators to commercial aviation to military communications. The second mechanism is solar energetic particles. These are protons, electrons, and heavier ions accelerated to tremendous speeds by the shock waves that precede coronal mass ejections. Unlike electromagnetic radiation, these particles have mass. They travel at significant fractions of the speed of light, but not at light speed itself. They typically arrive hours after the flare, though the fastest particles can reach Earth in as little as 15 minutes. Solar energetic particles are the primary radiation hazard during solar storms. The protons are particularly damaging because they can penetrate deep into spacecraft structures and human tissue. During major particle events, astronauts aboard the International Space Station shelter in the most heavily shielded sections. Even airline passengers on polar routes receive measurably elevated radiation doses. For satellites, solar energetic particles cause cumulative damage to electronics and solar cells. They also create secondary radiation through interactions with spacecraft materials. A proton striking a metal surface can generate a shower of secondary particles that spread damage throughout nearby components. The particle flux during a major event can exceed normal background levels by factors of thousands or even millions. Satellites designed to survive the typical space environment can find themselves overwhelmed. Safe mode offers some protection, but particles penetrate regardless of what software is running. The third mechanism is geomagnetically induced currents. This affects ground-based infrastructure rather than satellites directly, but the consequences for the space industry are profound. When a coronal mass ejection strikes Earth's magnetosphere, it compresses and distorts the magnetic field. This changing magnetic field induces electrical currents in any conductive path on or near Earth's surface. The longer the conductor, the larger the induced current. Power transmission lines, pipelines, undersea cables, and railroad tracks all become unwitting antennas, picking up currents they were never designed to carry. For power grids, geomagnetically, induced currents are existentially dangerous. The currents flow through transformers, saturating their magnetic cores and causing them to overheat. A transformer operating in saturation draws excessive current from the grid, generates harmonics that propagate to other equipment, and can fail catastrophically if the condition persists. The 1989 Quebec blackout demonstrated this mechanism. A relatively moderate geomagnetic storm induced currents in the Hydro-Quebec transmission system. Protective relays detected abnormal conditions and began tripping. Within 92 seconds, the entire grid collapsed. 6 million people lost power. The blackout lasted 9 hours. Modern grids have implemented protective measures since 1989. Operators can reduce power flows in vulnerable lines. They can install blocking devices that prevent induced currents from reaching transformers. They can monitor conditions in real time and respond to developing threats. But these measures have limits. They work for storms of moderate severity. They work when operators have warning and time to implement procedures. Against a Carrington-class event arriving with minimal warning, the protection would be inadequate. The fourth mechanism is ionospheric disturbance. The ionosphere is the electrically charged layer of atmosphere between roughly 50 and 600 miles altitude. It plays a crucial role in radio communication and navigation. Radio waves interact with the ionosphere in complex ways. Some frequencies are absorbed, others are reflected, enabling long-distance communication by bouncing signals off the ionosphere and back to Earth. Still others pass through with varying degrees of delay and distortion. The specific behavior depends on the frequency, the angle of propagation, and the current state of the ionosphere. GPS signals must pass through the ionosphere to reach ground receivers. The charged particles in the ionosphere slow the signals, slightly. Receivers correct for this delay using models of typical ionospheric conditions. During normal operations, these corrections work well. Position accuracy of a few meters is routine for civilian receivers. During geomagnetic storms, the ionosphere becomes chaotic. Electron density varies dramatically over short distances. Sharp gradients form and dissolve unpredictably. Patches of extreme ionization develop alongside regions of unusual depletion. The orderly structure that models assume is replaced by turbulent complexity. GPS corrections based on normal models become wildly inaccurate. Signals traveling through severely disturbed regions experience delays that the receiver cannot predict or compensate. Position errors grow from meters to tens of meters or more. In extreme cases, receivers cannot obtain valid positions at all. Single-frequency receivers, the type found in most consumer devices, are most affected. Dual-frequency receivers can largely correct for ionospheric. Delay by comparing how the two frequencies are affected differently. Professional surveying equipment and aviation systems use dual-frequency receivers for this reason, but the majority of GPS users worldwide rely on single-frequency devices. The economic impact of GPS degradation is difficult to quantify but certainly enormous. Precision agriculture loses efficiency, logistics companies lose tracking capability, emergency responders lose navigation. Financial systems that use GPS timing for transaction synchronization experience glitches. The invisible infrastructure of time and position that underpins modern commerce becomes unreliable. The fifth mechanism is spacecraft charging. In the disturbed magnetospheric environment during a storm, the plasma surrounding satellites becomes highly variable. Different parts of a spacecraft can accumulate different amounts of electrical charge depending on their material composition, surface properties, and exposure to the plasma environment. Surface charging occurs when electrons and ions from the surrounding plasma impact the spacecraft at different rates. Electrons typically move faster than ions, so surfaces often accumulate negative charge. In shadow regions or on insulating materials, this charge can build to high voltages. Internal charging occurs when high-energy electrons penetrate the spacecraft's skin and deposit charge inside components. Dielectric materials, used extensively in electronics, can accumulate charge over time until the voltage becomes high enough to cause breakdown. When the voltage differential between different parts of the spacecraft becomes too large, electrostatic discharge occurs. An arc of electricity jumps across the gap. This discharge can destroy sensitive circuits, trigger phantom commands, upset attitude control, corrupt memory, and cause cascading failures. Electrostatic discharge is unpredictable. Two identical satellites in similar orbits may experience very different charging environments depending on exactly where they are when disturbed plasma sweeps past. The randomness makes design mitigation difficult. Engineers can ground surfaces, provide discharge paths, and use charge-resistant materials, but complete protection is impossible. Each of these 5 mechanisms operates on different timescales, affects different types of equipment, and requires different countermeasures. Electromagnetic radiation arrives instantly and affects everything exposed. Solar energetic particles follow hours later, causing cumulative damage. Geomagnetically induced currents threaten ground infrastructure when the CME arrives. Ionospheric disturbance impairs navigation and communication for days after the event. Spacecraft charging creates risks throughout the disturbed period, and sometimes for days afterward. A major solar storm attacks on all fronts simultaneously. It is not a single threat, but a coordinated assault on every vulnerability we have created, and we have created many. The engineers who design satellites understand these threats. They build in protection where they can. They accept risk where they must. They make trade-offs between cost, mass, capability, and survivability. No satellite can be completely hardened against the worst the sun can deliver. The expense would be prohibitive. The mass would be prohibitive. The capability would be compromised. Commercial satellites are designed to survive the typical space environment with reasonable margin. They are not designed for worst-case events. The economic logic is compelling. Why spend an extra $100 million hardening a satellite against an event that might not occur during its operational lifetime? The probability of any individual satellite experiencing a Carrington-class event is low, but the probability that some satellite will experience such an event approaches certainty over time, and when it happens, it will not affect just one satellite, it will affect all of them, simultaneously. The economic logic that made sense for individual spacecraft becomes collective madness when applied to an entire orbital ecosystem. We have built a civilization dependent on machines that cannot survive the worst our own star can deliver. We have done so knowingly, accepting the risk in exchange for the benefits. We have bet that our luck will hold. The next chapter examines the warning systems we have built to extend that luck, the networks of sensors and satellites that watch the sun and predict its attacks, the forecasters who try to give us precious hours of warning before the storm arrives. They are our first line of defense, and they are not nearly enough. Chapter 8. The warning systems we depend on. In Boulder, Colorado, at the foot of the Rocky Mountains, a building that looks like any other government office holds the front line of Earth's defense against the sun. This is the Space Weather Prediction Center operated by the National Oceanic and Atmospheric Administration. Here, a small team of forecasters works around the clock every day of the year, watching for signs that our star is about to attack. The center occupies a peculiar position in the American bureaucracy. It is part of the National Weather Service, the same organization that predicts rain and hurricanes. But its subject matter is alien to traditional meteorology. Instead of pressure systems and jet streams, these forecasters track magnetic field configurations and coronal mass ejections. Instead of rain gauges and weather balloons, they rely on satellites positioned millions of miles from Earth. The primary sentinel is a spacecraft called the Deep Space Climate Observatory, or DSCOVR. It orbits at the L1 Lagrange point, roughly 1 million miles from Earth, directly between our planet and the Sun. At this location, the gravitational pull of the Sun and Earth balance in such a way that the spacecraft can maintain a stable position relative to both. From L1, DSCOVR has an unobstructed view of the Sun. Its instruments measure the solar wind continuously, sampling the particles and magnetic fields that stream past on their way to Earth. When a coronal mass ejection approaches, DSCOVR detects it directly. The spacecraft measures the density, speed, and magnetic orientation of the incoming plasma. This data is transmitted back to Earth at the speed of light. It reaches Boulder roughly 4 seconds after DSCOVR's instruments record it. The forecasters see what is coming roughly 30 to 60 minutes before it arrives at Earth. This is the warning window, 30 to 60 minutes to alert satellite operators, power grid managers, airlines, and anyone else who needs to take protective action. 30 minutes sounds like a reasonable amount of time, but consider what must happen in those 30 minutes. The DSCOVR data must be processed and analyzed. Forecasters must assess the severity of the incoming storm based on the measured parameters. They must issue warnings through official channels. Those warnings must reach the people who need to act. Decisions must be made. Actions must be taken. Satellite operators need to command their spacecraft into safe mode. This requires establishing communication with each satellite, uploading commands, and verifying compliance. For a constellation of thousands of satellites, this is not instant. Power grid operators need to reduce power flows in vulnerable lines, disconnect certain transformers, and prepare to shed load if necessary. These actions require coordination across control rooms, communication with field personnel, and careful execution to avoid creating new problems while solving old ones. Airlines need to reroute flights away from polar regions where radiation exposure is highest and communication most unreliable. Aircraft already airborne cannot simply turn around. New flight plans must be calculated, fuel loads assessed, and crews informed. 30 minutes is not enough time to do all of this perfectly. It is barely enough time to do it adequately, and 30 minutes assumes everything works correctly. DSCOVR is a single spacecraft. If it fails, the warning window shrinks dramatically. Ground-based observations can detect some solar activity, but they cannot measure the incoming CME directly. Forecasters would be reduced to making predictions based on observations of the Sun itself, hours or days earlier, rather than direct measurement of the approaching storm. The spacecraft is old. It was built in the 1990s as a climate observation mission, then placed in storage when that mission was cancelled. It was finally launched in 2015, nearly 2 decades after construction. The instruments are functional but aging. Replacement plans have faced funding challenges and delays. If DSCOVR fails before a replacement is operational, Earth's early warning system will have a critical gap. The forecasters in Boulder will still issue warnings based on solar observations, but those warnings will be less precise, less confident, and less actionable. Beyond DSCOVR, an array of other assets contributes to space weather monitoring. The Solar Dynamics Observatory stares at the Sun constantly from geosynchronous orbit, capturing images every 12 seconds in multiple wavelengths. It can detect solar flares as they occur, providing near-instant awareness of major eruptions. The GOES satellites, primarily known for weather imaging, also carry instruments that measure the space environment. They detect solar energetic particles and monitor the geomagnetic field, providing ground truth for what conditions are actually like in Earth's vicinity. Ground-based observatories track sunspots and solar activity, building the long-term context that helps forecasters understand what the Sun might do next. Magnetometer networks around the world measure changes in Earth's magnetic field, detecting the arrival of geomagnetic storms and assessing their severity. All of this data flows to Boulder, where it is integrated, analysed, and converted into forecasts and warnings. The system works. It has worked for decades. During the Ganon storm of 2024, the forecasters provided accurate warnings that enabled operators to prepare. The storm was severe but not catastrophic, partly because the warning system functioned as designed. But the system has limitations that become more severe as the threats become larger. The first limitation is timing. Even at L1, DSCOVR is only about 1% of the distance to the Sun. It detects CMEs at the last possible moment. For a typical storm, this provides roughly an hour of warning. For an exceptionally fast CME, the warning window shrinks to as little as 15 minutes. For a Carrington-class event where the CME might travel at over 2,000 km per second, the warning could be measured in tens of minutes rather than an hour. The second limitation is precision. Forecasters can tell that a CME is coming and estimate its approximate arrival time. They can measure the speed and density of the solar wind. But predicting exactly how severe the geomagnetic effects will be remains difficult. The crucial factor, the orientation of the magnetic field embedded in the CME, can change during transit. What DSCOVR measures at L1 may not be exactly what arrives at Earth. Forecasters use probabilistic language for this reason. They describe the chance of various outcomes rather than making definitive predictions. This uncertainty makes it harder for operators to decide how aggressively to implement protective measures. Overdoing protection has costs. Underdoing it has risks. The third limitation is coverage. Space weather forecasting depends on infrastructure that is itself vulnerable to space weather. DSCOVR could be damaged by the very events it is designed to detect. The communication links that carry its data back to Earth pass through the ionosphere and could be disrupted during severe storms. The ground systems that process the data require electricity. If a truly severe storm arrived, the warning system might degrade precisely when it was most needed. Forecasters have backup plans and redundant communications, but a Carrington-class event would stress all of those backups simultaneously. The fourth limitation is response capability. Even perfect warnings are useless if the people receiving them cannot act. Satellite operators can only protect their spacecraft if they have the communication links and command authority to do so. Power grid operators can only implement protective measures if their systems are designed to be protected. Airlines can only reroute flights if alternative routes exist. For some threats, warning enables effective response. For others, warning merely tells us what is about to happen without providing any way to prevent it. A Carrington-class event would likely fall into the second category for many assets. There is no way to harden a satellite against extreme radiation after it has been launched. There is no way to install transformer protection devices during the 15 minutes before a CME arrives. Warning becomes simply awareness of impending loss. Despite these limitations, the space weather forecasting community continues to improve its capabilities. New models incorporate better physics. Machine learning techniques help identify patterns in historical data. International cooperation enables data sharing from observatories around the world. The European Space Agency is developing the Vigil mission, which will place a spacecraft at the L5 Lagrange point, trailing Earth in its orbit around the Sun. From this position, Vigil will have a side view of CMEs heading toward Earth, enabling better prediction of their characteristics. It will also provide backup coverage if L1 assets fail. NASA and NOAA are working on next-generation space weather, satellites. These would carry improved instruments with better sensitivity and faster data transmission. They would extend the warning window and improve forecast precision, but these missions take years to develop and launch. Funding is always uncertain. Political priorities shift. The UN does not wait for bureaucratic timelines. The fundamental problem is that space weather forecasting is under-resourced relative to its importance. The entire budget for space weather monitoring and prediction is a tiny fraction of what is spent on terrestrial weather services. Yet the potential consequences of space weather, damage to satellites, disruption of power grids, interruption of navigation and communication, rival or exceed the impact of the worst hurricanes. The Ganon storm of 2024 demonstrated both the strengths and weaknesses of the current system. The forecasters saw it coming. They issued accurate warnings. Operators took protective action. The outcome, while disruptive, was manageable. But the Ganon storm was not a worst-case event. It was not even close to Carrington class. It was simply the strongest storm in 2 decades, a reminder that the sun can indeed cause trouble, while falling far short of demonstrating just how much trouble is possible. The next severe storm will test the warning system again. The next Carrington-class event will test whether warnings matter at all when the threat exceeds our ability to respond. The forecasters in Boulder know this. They watch their screens and track the active regions and hope that when the big one comes, their warnings will make a difference. The next chapter examines what happens if those warnings fail, or if they succeed but the storm is simply too powerful. What does a world without satellites actually look like? The answer may surprise you. Chapter 9. What happens if we lose our satellites? Imagine waking up tomorrow to find that every satellite in orbit has gone silent. Not damaged, not degraded, simply gone. What would your day look like? The first thing you might notice is your phone. The map application cannot locate you. The blue dot that normally shows your position just spins and fails. Navigation is unavailable. You know the way to work, probably, but the exact traffic conditions are unknown. The app cannot tell you about accidents ahead or suggest faster routes. You check the weather. The forecast is there, sort of. But it is oddly vague. The satellite imagery that normally shows cloud formations in real time is absent. The forecast is based on ground stations and mathematical models, the way it was done in the 1960s. It is less precise. It extends only a few days instead of a week or more. If a hurricane is forming in the Atlantic, you might not know until it reaches shore. You turn on the news, something is wrong. The broadcast is not live from distant locations. The correspondent in London is not connected in real time. International news is delayed, arriving when physical recordings can be transmitted through undersea cables. The instant global awareness you took for granted has vanished. You try to make a phone call to a friend in another country. The call fails. International communication depends heavily on satellite links, especially for regions without robust undersea cable connections. Some routes still work, many do not. The internet is slower and spottier. Large portions of the world are effectively offline. You drive to work, navigating by memory and road signs. The GPS-guided trucking industry is in chaos. Logistics companies cannot track their shipments. Deliveries are delayed or lost. The just-in-time supply chain, which depends on precise tracking and coordination, begins to unravel. At work, you discover that financial transactions are failing. The timestamps that authenticate trades and transfers are normally provided by GPS atomic clocks, distributed across the global network. Without those timestamps, systems cannot verify that transactions occurred in the correct sequence. Trading halts. Banks freeze accounts pending manual verification. The wheels of commerce grind toward a stop. This scenario is hypothetical but not fantastical. It describes the first day after a complete satellite failure. The second day would be worse. The second week would be worse still. Modern civilization has grown dependent on satellites in ways that most people never consider. The dependency crept up on us over decades. Each new application seemed modest and reasonable. Navigation, communication, weather forecasting, timing synchronization. Each one added value. Each one created dependency. Today, the cumulative dependency is profound. Studies have attempted to quantify the economic value of satellite services to the American economy alone. The estimates reach into the trillions of dollars annually. Navigation services alone contribute hundreds of billions in economic value through efficiency gains in transportation, agriculture, construction, and emergency response. But economic value understates the true importance. Some services are not merely valuable, they are essential. Without them, systems fail that cannot be easily restarted. Consider precision agriculture. Over the past 2 decades, farming has been transformed by GPS guidance. Tractors follow satellite-directed paths with centimeter accuracy. Seeds are planted in optimal patterns. Fertilizer and pesticide are applied exactly where needed, no more and no less. The efficiency gains have been enormous. Yields are higher, costs are lower, environmental impact is reduced. Remove GPS, and modern farms cannot simply revert to older methods. The equipment has changed, the skills have changed. Farmers who grew up with satellite guidance may not know how to cultivate fields the way their grandparents did. The transition back would take years and cost productivity throughout. Consider aviation. Commercial air travel depends on satellite navigation and communication. Aircraft crossing oceans stay in contact through satellite links. They navigate using GPS rather than older ground-based systems. Air traffic control coordinates thousands of flights simultaneously using data that flows through satellite networks. Without satellites, aviation does not stop. But it slows dramatically. Aircraft must follow older, less efficient routes. Communication gaps force greater separation between planes. Flight times increase. Capacity decreases. The global air transport system that moves billions of passengers annually becomes a shadow of itself. Consider disaster response. When hurricanes strike or earthquakes hit, satellites provide the first detailed imagery of the damage. Rescue teams use GPS to navigate to survivors. Communication satellites link responders in the field, with coordinators managing resources. Without these tools, disaster response reverts to methods from the mid-20th century. More people die. Consider military operations. Modern warfare is built on space-based assets. Surveillance satellites provide intelligence. Communication satellites link commanders with forces in the field. Navigation satellites guide weapons with precision measured in meters. Early warning satellites detect missile launches within seconds. A nation that loses access to space loses its ability to project power effectively. The American military in particular has become so dependent on space that the loss of satellites would be strategically catastrophic. Adversaries know this. The vulnerability is not secret. The scenario of losing all satellites simultaneously is extreme. It would require a catastrophe beyond any we have experienced. But partial losses are not only possible, they are likely. A severe solar storm would not destroy every satellite instantly. It would degrade capability unevenly. Some satellites would fail immediately, others would be damaged, but continue operating with reduced capability. Still others would survive largely intact but be unable to communicate through the disrupted ionosphere. The result would be chaos rather than simple absence. Systems designed for reliability would suddenly become unreliable. Operators would struggle to determine which assets were functional. Users would face intermittent outages that came and went unpredictably. The infrastructure would not be gone, it would be broken. Broken infrastructure may be worse than absent infrastructure. When something is simply gone, people adapt. They find alternatives or do without. When something is intermittently functional, people try to use it anyway. They make plans based on capability that may not be there when needed. They defer the difficult work of finding alternatives because the familiar system still mostly works. The Ganon storm provided a small taste of this dynamic. GPS degraded but did not fail completely. Farmers could still use their guidance systems in some locations at some times. They could not rely on them consistently. Some pushed forward anyway and suffered the consequences. Others delayed their work, losing precious planting days. Satellite communication remained functional but unreliable during the storm. Some links worked normally, others failed intermittently. Users could not predict which category their connection would fall into until they tried. This unpredictability is itself damaging. Efficiency requires predictability. When you cannot trust that a system will work, you must build in redundancy and margin. That redundancy costs money and time. The seemingly invisible benefit of satellite infrastructure includes the predictability it provides. Remove that predictability, and costs rise throughout the economy. Now consider the longer-term implications of a major satellite loss event. Replacement takes time. Building satellites requires specialized factories. Launching them requires rocket infrastructure. Deploying and commissioning them requires ground control systems. All of these have limited capacity. The satellite industry has grown accustomed to steady expansion. Factories produce at rates calibrated to planned demand. Launch capacity is allocated years in advance. If a storm destroyed or damaged hundreds of satellites simultaneously, the industry could not simply replace them quickly. The queue would extend for years. During those years, humanity would operate with degraded capability. Navigation would be less precise. Communication would be spottier. Weather forecasting would be cruder. The conveniences and efficiencies we have grown accustomed to would be diminished. Some argue this might be healthy, that we have become too dependent on technology, that a period of reduced capability would force us to develop resilience and alternatives. This argument has superficial appeal but ignores reality. The systems we have built are not luxuries, they are load, bearing elements of civilization. Removing them does not simplify our lives, it degrades them in ways that cause real suffering. Precision agriculture is not a convenience. It is how we feed 8 billion people without destroying the remaining wild lands. Lose it, and either yields fall or more land must be cultivated. Modern logistics is not a convenience. It is how goods reach markets efficiently enough to keep prices affordable. Lose it, and supply chains collapse. Store shelves empty, prices spike. The most vulnerable suffer most. Global communication is not a convenience. It is how we maintain the connections that enable international cooperation. Lose it, and the world becomes more fragmented, more suspicious, more dangerous. We cannot go back to 1960. The world of 2026 cannot be supported by the infrastructure of 1960. There are too many people. The systems are too interconnected. The complexity is too great. The only path forward is through. We must protect the infrastructure we have built. We must prepare for the storms that threaten it. We must develop resilience and redundancy, not as alternatives to satellite dependency, but as reinforcements of it. The final chapter examines what preparing for the inevitable actually looks like. The policies, technologies, and investments that could make the difference between disruption and catastrophe. The choices we must make as a civilization if we wish to survive what the sun will eventually deliver. Time is running out. The sun is waking up, and our satellites are waiting in its path. Chapter 10. Preparing for the inevitable. The sun will attack again. This is not pessimism. It is physics. The magnetic dynamo at the heart of our star will continue to generate storms for billions of years. Some of those storms will be moderate. Some will be severe. Eventually, one will be catastrophic. The question is not whether humanity will face a Carrington-class event in the space age. The question is whether we will face it prepared or vulnerable. Right now we are vulnerable, but we do not have to remain so. Preparation begins with awareness. Most people have never heard of the Carrington event. Most people do not know that solar storms can damage satellites and power grids. Most people do not understand how dependent their daily lives have become on space-based infrastructure. This ignorance is dangerous because it prevents the political will necessary for investment in protection. Education is the first step. When voters understand the threat, they can demand that their governments address it. When corporate boards understand the risk, they can allocate resources for resilience. When engineers understand the problem, they can design solutions. The Ganon storm of 2024 helped raise awareness. The dramatic Aurora photographs spread across social media. News articles explained what had happened. Scientists gave interviews discussing the implications. But the impact was modest because the damage was modest. A near miss does not concentrate the mind the way a direct hit does. Waiting for a direct hit to motivate action is a poor strategy. By definition, the preparations that could have helped will not have been made. The better approach is to act now while we have the luxury of time. The most critical priority is protecting the power grid. Electricity is the foundation of everything else. Without it, communication fails, transportation halts, water stops flowing, medical equipment goes dark, social order deteriorates rapidly. The vulnerability of power grids to geomagnetically induced currents is well understood. The solutions are known. Blocking devices can be installed at transformer stations to prevent induced currents from flowing through sensitive equipment. These devices are not particularly expensive relative to the cost of the infrastructure they protect. They are simply not installed widely enough. Regulatory frameworks exist to encourage or require such protection, but enforcement varies. Some utilities have invested significantly in resilience, others have not. The result is a patchwork of vulnerability where some regions are protected and others are not. Federal mandates requiring minimum levels of protection would create consistency. Standards should specify what level of geomagnetic disturbance transformers must survive. Utilities that fail to meet those standards should face consequences. The alternative is hoping that severe storms happen to strike regions that have voluntarily chosen to prepare. Beyond blocking devices, grids need operational procedures for storm response. Operators must know how to recognize developing geomagnetic conditions. They must have authority to implement protective measures, including reducing power flows and disconnecting vulnerable equipment. They must practice these procedures regularly so that when an emergency arrives, the response is automatic. The North American Electric Reliability Corporation has developed standards for geomagnetic disturbance protection. These standards are a good start but may not be sufficient for a truly extreme event. Continuous improvement based on new research and lessons from actual storms is essential. Spare transformer capacity is another crucial investment. Large power transformers are custom-built, expensive, and slow to manufacture. The existing supply chain cannot respond quickly to mass failures. Utilities should maintain strategic reserves of critical transformer types. Governments should support domestic manufacturing capacity so that rebuilding does not depend on overseas suppliers. For satellites, the calculus is different. Spacecraft already in orbit cannot be retrofitted with better shielding. The protection must be designed in before launch. This requires satellite operators to accept higher costs for hardening, knowing that the probability of any individual satellite experiencing a catastrophic storm is low. One approach is regulatory requirements for minimum radiation hardness in satellites operating in certain orbits or providing critical services. Navigation satellites, communication satellites serving emergency services, and weather satellites could be required to survive specified storm conditions. This would increase costs but also increase reliability. Another approach is insurance incentives. Insurers could offer better rates for satellites that meet higher hardening standards. Operators would then face a financial incentive to build more robust spacecraft. The insurance industry already considers space weather risk in its underwriting. Formalizing standards could amplify this effect. For mega constellations like Starlink, the economics are different. These constellations depend on launching large numbers of relatively inexpensive satellites. Heavy radiation hardening would undermine the business model, but the sheer number of satellites provides a form of resilience. If a storm destroys 10% of the constellation, the remaining 90% can continue operating while replacements are launched. The key is maintaining spare production and launch capacity. Operators should stockpile satellites ready for rapid deployment. Launch providers should have surge capability to respond to emergencies. Ground control systems should be designed to incorporate new satellites quickly. Early warning systems deserve continued investment. The DSCOVR spacecraft at the L1 point is aging. Replacement missions are planned but face funding uncertainty. Allowing a gap in coverage would be foolish economy. The warning time DSCOVR provides is essential for implementing protective measures. The Vigil mission at L5 will provide valuable complementary observations. Other nations are developing their own space weather monitoring capabilities. International cooperation can ensure that data is shared globally, benefiting everyone regardless of which nation operates a particular sensor. Forecast models continue to improve. Machine learning techniques can identify patterns in historical data that human analysts might miss. Physics-based simulations grow more accurate as computing power increases and scientific understanding advances. Investment in research pays dividends in better predictions, but forecasting has fundamental limits. No model can perfectly predict what the sun will do. No sensor can measure every relevant parameter. Decision makers must accept uncertainty and plan accordingly. This means implementing protective measures based on probability assessments rather than waiting for certainty. Ground-based backup systems for satellite services offer another layer of resilience. Navigation can be supplemented by terrestrial positioning systems. The E-LORAN system, an enhanced version of the old LORAN technology, can provide positioning accurate enough for many applications during GPS outages. Multiple nations have invested in such systems, more should. Communication can be supplemented by expanded undersea cable capacity in terrestrial networks. The internet was originally designed to survive nuclear attack by routing around damage. Some of that resilience has been lost as traffic has concentrated through satellite links and key exchange points. Diversifying paths and adding redundancy would improve robustness against multiple threats, including solar storms. For timing synchronization, ground-based atomic clocks can provide local references when GPS timing is unavailable. Critical infrastructure, including power plants, financial systems, and telecommunications networks, should maintain independent timing capability rather than depending entirely on space-based sources. International cooperation is essential because space weather is a global phenomenon. A storm that damages American satellites also damages Chinese satellites. A storm that threatens European power grids also threatens Asian power grids. No nation can protect itself alone. The United Nations Committee on the Peaceful Uses of Outer Space has addressed space weather in its deliberations. The International Civil Aviation Organization has incorporated space weather into its standards for aviation safety. The International Telecommunication Union coordinates frequency assignments that affect resilience to ionospheric disruption. These frameworks provide foundations for deeper cooperation. Nations could agree to share space weather data openly and in real time. They could coordinate on minimum standards for satellite hardening. They could establish protocols for mutual assistance during severe events. They could jointly invest in monitoring systems too expensive for any single nation. The private sector has a role beyond simply building more resilient products. Companies that depend on satellite services should understand their vulnerabilities and develop contingency plans. They should test those plans regularly. They should pressure their suppliers to provide resilient systems. They should share lessons learned with their industries. Individual citizens have limited ability to prepare for satellite failures directly, but they can reduce their personal vulnerability to the cascading effects. Maintaining emergency supplies of food, water, and medicine provides buffer against supply chain disruptions. Knowing how to navigate without GPS, even using simple paper maps, could matter during extended outages. Understanding that services may become unreliable helps manage expectations and reduce panic. The ultimate preparation is philosophical. Humanity must accept that it exists in a dangerous universe. The sun that makes life possible also poses threats. We are not entitled to stability. We must earn it through foresight and effort. The space age is barely 60 years old. In that brief span, we have become utterly dependent on machines orbiting overhead. We have done so without fully acknowledging the risks. We have enjoyed the benefits while ignoring the vulnerabilities. The Ganon storm of 2024 was a reminder. It was not a catastrophe. It was a warning. The aurora that danced over Florida and Mexico was beautiful. It was also a symptom of forces that could, under different circumstances, have caused immense damage. The sun is not our enemy. It is simply what it is: a nuclear furnace, a generator of light and heat and particle radiation and magnetic disruption. It has been doing what it does for 4.5 billion years. It will continue for billions more. We are the newcomers. We have built our civilization in the light of this star without understanding its nature. We have placed our most critical infrastructure in the path of its storms without adequate protection. We have grown complacent during a period of relative quiet. That quiet is ending. Solar cycle 25 is building toward maximum. Activity is higher than predicted. The sun is waking up. Somewhere in the churning plasma of the solar corona, magnetic field lines are tangling. Energy is accumulating. The next great storm is forming. It might arrive this year. It might arrive next decade, but it will arrive. When it does, the choices we make now will determine the outcome. We can prepare and endure. We can adapt and recover. Or we can ignore the warnings and suffer the consequences. The satellites overhead are waiting. The power grids below are humming. The forecasters in Boulder are watching their screens. The sun is doing what it has always done. The question is not what the sun will do. The question is what we will do. If you found this investigation valuable, please like this video and subscribe to the channel. Tell me in the comments what you think we should prioritize in preparing for the next great solar storm. Should we focus on protecting power grids, hardening satellites, building backup systems, or accepting that some events are beyond our control? The sun is not waiting for our answer, but perhaps that answer matters anyway. Thank you for watching. I will see you in the next investigation.